There is something strange about the moon's south pole. From orbit, it looks like the rest of the lunar surface, gray, cratered, ancient. But certain craters there have not seen sunlight in billions of years. Not a single photon has touched their floors since before complex life existed on Earth. And in that darkness, something has been accumulating. Something that, by every reasonable expectation, should not be there. Water. Not as a curiosity, not in trace amounts easily dismissed. 600 billion kilograms of it, by current estimates. Roughly the mass of every car on Earth, frozen into the regolith of a world with no atmosphere, no magnetic field, no obvious mechanism for keeping it there. The question of how it arrived and where exactly it hides is one of the stranger scientific detective stories of the last half-century. It involves crashed spacecraft, disagreements between datasets, a $75 million rover that looked directly at the ground and found nothing, and a camera so sensitive it can photograph rooms that have not seen light since the Precambrian. What follows is a story of how we came to suspect the moon has water, and why, the closer we look, the harder it becomes to find. The Soviet Union's Luna 24 mission landed on the moon in 1976. It was a robotic probe of considerable ambition. It drilled 2 meters into the lunar surface, collected 170 grams of soil, and returned it to Earth intact. Among the findings was an anomaly. Approximately 0.1% of the sample was water. More intriguingly, the concentration increased with depth. It was dismissed. Water contamination from Earth during sample return was a known problem. The Apollo missions had shown trace water before, and that too had been attributed to contamination. The question was filed away rather than resolved. It would remain filed for nearly 2 decades. In 1994, NASA's Clementine mission changed the terms of the discussion. Its orbital mapping revealed something that hadn't been clearly established before. Permanently shadowed regions exist near the moon's south pole, craters whose geometry and the moon's low axial tilt of just over 1 degree combine to ensure the sun never reaches their floors. Never, in billions of years of lunar history, not once. At those steps, temperatures were estimated to sit below -173 degrees Celsius, cold enough, theoretically, to trap and hold water ice indefinitely. The implications were significant. If comets had struck the moon over its history, and there is strong evidence they did, water delivered by those impacts could have migrated to these cold traps and stayed there, protected, preserved, waiting. NASA responded by launching the Lunar Prospector in 1998, specifically to hunt for evidence of this ice. Using spectroscopy from orbit, it detected large concentrations of hydrogen at both poles. The math on paper was suggestive. Somewhere between 10 and 300 million tons of water ice might be scattered in craters across the polar regions. But hydrogen is not water. It could equally indicate hydroxyl, OH, water's closest chemical relative, a molecule short of the thing scientists were actually looking for. The prospector couldn't distinguish between them. In 1999, the spacecraft was deliberately crashed into the South Pole. The plan was straightforward. A large enough impact would kick debris into sunlight, where Earth-based observatories could use spectroscopy to identify water vapor in the cloud. It was a reasonable approach. It didn't work. No water was detected. Japan's SELEN mission tried a similar approach in 2007, high-resolution imaging of the moon, followed by a deliberate crash into the South Pole designed to produce an analyzable debris plume. Again, nothing definitive. The mystery had accumulated more data and more failed attempts, but no resolution. India's Chandrayaan-1 mission, launched in 2008, took a different approach. Rather than relying on Earth-based telescopes to analyze debris from a distance, it deployed an impactor designed to descend close to the lunar surface and detect water vapor through spectroscopy in real time, as it fell. The probe was released. It descended for 25 minutes. It crashed near a crater at the South Pole. In the data it transmitted back during those 25 minutes was something scientists had been looking for since the 1970s, a confirmed signature of water. A few months later, the Moon Mineralogy Mapper instrument aboard the same spacecraft, operating from orbit, independently confirmed the presence of water on the lunar surface. 2 instruments, 2 methods, same answer. NASA wanted more proof. Their Lunar Crater Observation and Sensing Satellite, LCROSS, was designed to produce it definitively. The mission architecture was deliberately simple. The upper stage of the Atlas V rocket that launched LCROSS was left attached to the spacecraft during transit and then released to crash into a permanently shadowed crater at the South Pole. The resulting debris plume rose above the crater rim into sunlight, vaporizing trapped ice and other compounds. LCROSS itself then flew directly through this plume, sampling it with onboard instruments before it too crashed into the moon. The Lunar Reconnaissance Orbiter, already in position above the surface, studied the aftermath. The data was unambiguous. The hydrogen concentrated at the lunar poles does indeed belong to water ice crystals. The debate, at least in its oldest form, was over. But a different, more precise set of questions was just beginning. LRO continued mapping the surface, and it found something no one had quite anticipated. Water wasn't only hiding in permanently shadowed craters, it was present in trace amounts across the top layer of regolith on the broader lunar surface. The whole moon, it appeared, was faintly, almost imperceptibly damp. More strangely still, this wetness seemed to move. Around lunar noon, when surface temperatures peaked, the water appeared to dissipate. By evening, it returned. A lunar water cycle of sorts. Not rivers, not lakes, not anything visible, but a chemical rhythm responding to temperature and radiation. Several mechanisms have been proposed for this. Micrometeorites constantly rain down on the moon, some carrying water, depositing it on impact. The solar wind delivers hydrogen ions to the surface, which react with oxygen-bearing minerals in the soil to produce hydroxyl, and micrometeorite bombardment may then be converting that hydroxyl into water. The resulting molecules might then become trapped in tiny glass beads formed by the heat of impacts, or sheltered between grains of regolith, shielded from sunlight. The exact mechanism remains unclear, but the implication for future colonization was significant. If water could be accessed across the broader lunar surface, not just within permanently shadowed craters, the viable locations for a lunar base expanded considerably. The discovery didn't simplify things, it complicated them. The cold we weren't prepared for. LRO's Diviner instrument, 7 thermal infrared channels designed to measure surface temperature, returned readings that surprised even researchers who had expected extreme conditions. At the equator, the moon swings between 120 degrees Celsius in direct sunlight and negative 130 degrees Celsius at night. The poles were expected to be colder, but one crater measured by Diviner registered temperatures of negative 250 degrees Celsius. That is the coldest temperature ever measured on any object in the entire solar system. Colder than the surface of Uranus, colder than Neptune, colder than Pluto. These temperatures would preserve not just water ice, but a range of other volatile compounds: carbon dioxide, carbon monoxide, dinitrogen, argon. A cold trap at negative 250 degrees Celsius is, in a sense, a deep freezer that has been running for billions of years, accumulating whatever the solar system has happened to deliver. In 2020, NASA's SOFIA, the Stratospheric Observatory for Infrared Astronomy, an airborne telescope operating above most of Earth's atmosphere, extended the picture further. It detected water in the sunlit surface of Clavius crater, one of the largest craters visible from Earth. The concentration was between 100 and 412 parts per million. For context, the Sahara Desert holds approximately 100 times more water per unit volume than this. It is an extraordinarily small quantity, but its presence in a sunlit location confirmed that water on the moon is not confined to the coldest, darkest places. The distribution of lunar water was proving stranger and more diffuse than the original hypothesis had predicted. Water is sometimes called the oil of space. The phrase is not hyperbole. The core problem of deep space exploration is mass. Every kilogram launched from Earth's surface requires propellant to lift it, and propellant has mass of its own, which requires more propellant. in a compounding relationship that makes ambitious missions extraordinarily expensive. Getting to low Earth orbit costs roughly $2,000 to $10,000 per kilogram, depending on the launch system. Getting further costs progressively more. The moon has 1/6 of Earth's gravity. Launching material from the lunar surface into space requires a fraction of the energy needed to launch the same mass from Earth. And while the moon is 380,000 kilometers away, the orbital mechanics are such that delivering payload from the lunar surface to low Earth orbit can actually be less resource intensive than launching it from the ground. Water ice on the moon can be electrolyzed into hydrogen and oxygen, the two most commonly used rocket propellants. A lunar fuel depot would mean that missions departing from Mars, the asteroid belt, or elsewhere in the outer solar system could refuel in lunar orbit rather than carrying everything from Earth. The mass savings compound across every mission that follows. Beyond propulsion, water means drinking water, means agriculture, means oxygen for habitation. A lunar base that can extract local water is a base that doesn't need to import one of its most critical resources across hundreds of thousands of kilometers. The stakes around finding, locating, and extracting this water are consequently very high. Multiple space agencies have made it a central objective of their next decade of lunar operations. NASA's Artemis program is targeting the South Pole. China and Russia are planning a joint robotic station there by 2030. The south pole of the moon is suddenly, quietly, becoming one of the most strategically significant pieces of real estate in the solar system. And no one has yet seen the water with their own eyes. South Korea's Danuri spacecraft entered lunar orbit in December 2022, the seventh nation to achieve that milestone. NASA contributed an instrument to the mission, ShadowCam, a camera 200 times more sensitive than LRO's standard narrow-angle camera, specifically designed to photograph permanently shadowed regions. The first images from ShadowCam of Shackleton Crater, a landmark at the moon's south pole, one of the primary candidate sites for subsurface ice, were remarkable for their clarity. For the first time, scientists could see the floor of a permanently shadowed crater with genuine resolution. It looked like the rest of the moon, hummocky ground, the trail of a boulder that had rolled down the crater wall, a track potentially billions of years old, preserved perfectly in the windless vacuum. No ice, no frost, no glint. ShadowCam has since imaged many craters across both polar regions. In none of them has it found the visual signature of water ice, not glaciers, not frost, not a surface dusting. And this is confusing because Chandrayaan-1 detected water there, from orbit, using spectroscopy. The signal is in the data, but looking directly at the place where that data says water should be, you see nothing. India's Chandrayaan-3 mission, which successfully landed at the lunar South Pole in August 2023, was the first spacecraft ever to do so. The achievement was historic in multiple respects. India became the fourth nation to land on the moon and the first to reach its South Pole. The mission was also, by the standards of contemporary space exploration, strikingly inexpensive. The Artemis program cost billions of dollars per launch. Chandrayaan-3's total mission budget was approximately $75 million. The lander, Vikram, deployed a 6-wheeled rover called Pragyan, which carried 2 instruments for in situ chemical analysis, an alpha particle X-ray spectrometer, and a laser-induced breakdown spectroscopy device. Together, these could identify the elemental composition of whatever material the rover encountered. Over 2 weeks, the duration of a lunar day, after which temperatures would drop to minus 120 degrees Celsius, beyond what the hardware was designed to survive, Pragyan analyzed the surface around the landing site. It found aluminum, calcium, iron, chromium, titanium, oxygen. The first in situ confirmation of sulfur at the lunar pole, which carries implications for the moon's volcanic history. What it did not find was hydrogen. Pragyan traveled approximately 100 meters from the lander over its operational lifetime. It encountered a 4-meter crater and navigated around it. It encountered a second crater and went around that one too. No images from the interior of either crater are available. The mission was declared a success, and it was. The data on sulfur, temperature gradients, and plasma conditions in the lunar atmosphere is genuinely valuable. But the thing Israel had announced as the primary objective, evidence of water, was absent from Pragyan's findings. This sits uneasily alongside Chandrayaan-1's detection. Vikram carried a temperature sensor called Shaste. It could take readings at the surface and at 1 centimeter increments down to a depth of 10 centimeters. At the surface, the temperature was approximately 60 degrees Celsius, uncomfortably hot, the result of direct solar heating of the top layer of regolith. 8 centimeters down, it was negative 10 degrees Celsius. That's a 70-degree drop across less than the width of a hand. Lunar regolith is an extraordinarily poor conductor of heat. The top layer heats and cools dramatically with the position of the sun. Beneath that layer, just centimeters down, temperatures are largely insulated from what's happening at the surface. The implication is significant. If water ice exists at the South Pole, and the orbital spectroscopy data suggests it does, it may not be sitting at the surface where landers and rovers and sensitive cameras can see it. It may be buried, protected by the same insulating properties of the regolith that make the temperature gradient so steep. If that's correct, then the absence of visual ice and shadow cam's images, and the absence of hydrogen and Pragyan's surface level analysis would not mean there's no water. It would mean we've been looking in the wrong layer. Several obstacles stand between current understanding and actual extraction. The electrical environment at the poles is one. The lunar surface has no magnetosphere. Solar wind, a stream of ions and electrons, hits it directly. At crater edges and the terminator region, the geometry creates a separation between fast-moving electrons and slower-moving ions that can charge crater surfaces to hundreds of thousands of volts. Any equipment operating there without properly dissipative materials would be at serious risk of catastrophic discharge. Regolith itself is another. The fine dust is electrostatically charged. It adheres to everything: suits, instruments, optical surfaces. During the Apollo missions, astronauts reported regolith coating their suits so thoroughly it became impossible to clean. It is abrasive, it damages seals, and it is toxic when inhaled. Designing suits and equipment that can operate in that environment without degrading is an unsolved engineering problem. NASA had been developing a mission, the Volatiles Investigating Polar Exploration Rover, or VIPER, specifically designed to drive into permanently shadowed regions and drill below the surface to assess subsurface ice. It was, for several years, the most capable planned mission for actually locating the ice that the orbital data predicts. In July 2024, NASA canceled it. Budget pressures and construction delays had pushed the launch back repeatedly. The rover, already built, may be repurposed for spare parts. No comparable American mission is currently scheduled. The scientific community's response to the cancellation was pointed. It was called by some researchers a dark day for lunar science, not merely because the rover won't fly, but because no other mission over the coming years has VIPER's combination of mobility and subsurface access. The water is almost certainly there, 600 billion kilograms of it by the best current estimate. But the closer we look at the surface, the more the ice recedes, not disappearing, just retreating beneath the layer we can currently reach, into a coldness and darkness we are not yet equipped to fully probe. There is something worth pausing on in this history. The detection of water on the moon was, when it finally came in 2008, treated as a discovery. And it was. But in the 15 years since, the response has been more equivocal than the initial announcement suggested. Orbiter detect the signature from above. Landers find nothing at the surface. Sensitive cameras peer into craters that should be coated in ice and see bare regolith. This is not contradiction. It is a measurement problem, a gap between the orbital perspective and the ground level one, between what spectroscopy sees at scale and what a rover encounters at one specific patch of ground. But it is also a reminder that knowing something exists and knowing where to find it are different kinds of knowledge. The moon is 250,000 miles away, and we have touched perhaps a dozen points on its surface in human history. The temperature readings from Chandrayaan-3 may have identified the resolution. The ice is subsurface. It's sheltered by regolith from the very instruments designed to detect it. To find it, someone will need to drill, and to drill in a permanently shadowed region at -250°C under hundreds of thousands of volts of potential electrical charge in a dust environment that abrades through any material not specifically engineered for it, someone will first need to solve several engineering problems that are currently without solutions. The water is there. The question is whether we are capable of reaching it. That answer will not come from orbit.